So without further ado, I'd like to introduce Bill Dunham, who will speak about Euler.
Well, thank you, Jim. Pleasure to be here this evening to talk about Euler, my favorite mathematician, someone who's on everybody's short list of one of the greatest mathematicians of all time. So here he is. That is Euler. The official title of this portrait is the Hahnemann portrait, after the artist who did it. The unofficial title is Euler Emerging from the Shower. You know, if the portrait painter were coming over, I don't think I'd wear this, but that's what he decided to wear. Here's what I want to do tonight. Break this talk into three parts. Give a brief biography, so you have some dates to hang his life on. Give a survey, a broad survey of half a dozen or so of his great achievements, but without the mathematical detail, but just to give you a sense of the breadth and the depth of his legacy. And third, I actually want to show you an Eulerian proof with all the mathematical detail involved, so we can look over his shoulder and watch him work. Now, before you get scared, the prerequisites to this are just high school math. You don't have to be a Harvard graduate student to understand the mathematics, but I predict that people are going to leave here impressed with what he could do when he got going. So that's the goal. It's a busy agenda. Let's start with the biography, and here it is in a nutshell. Euler was born in 1707 in Basel, Switzerland. Last year was his tercentenary. People were celebrating all over the world. In 1720, this very bright young lad was off to study with Johann Bernoulli, a name you might know, one of the members of the great Bernoulli family. Bernoulli was in Basel, and Euler would go and study with him. Bernoulli gave him direction, gave him guidance, gave him mentorship. In 1722, Euler graduated from the University of Basel, and if you get out your calculator, you'll see he was 15 at the time. Pretty good. In 1727, he's off to St. Petersburg, to the academy at St. Petersburg. And remember, in those days, the great courts of Europe were surrounded by these academies. There was the Royal Society in London, the Paris Academy, the Berlin Academy, and Russia wanted its own. So there was this new academy at St. Petersburg, and Euler went there to help give luster to the court, to the monarch, to the nation. He stays there until 1741 when he goes to the Berlin Academy, which was then being run by Frederick the Great. And he plopped down there. He was like a free agent, went to another team. Stayed there until 1766 when he's back to St. Petersburg, and stayed in St. Petersburg until his death in 1783. Euler was buried in St. Petersburg. Subsequently, he was buried in Leningrad, and today he's buried in St. Petersburg. So it's amazing. Now, these dates make him almost the exact contemporary of Benjamin Franklin. So if you want to sort of compare him to someone from this side of the ocean, think Ben Franklin. These are almost exactly the same lifespan. On the personal side, he was married. He and wife Katharina had 13 children. But unfortunately, with the child mortality being what it was in the 18th century, only 5 of these children made it to adolescence. So it would have been a great deal of heartache in the Euler family. He had, by all accounts, a phenomenal memory. Euler could memorize anything: books, plays, tables. You know, most people have to look up logarithms, but if you can memorize them, that makes it a lot quicker. And this memory would serve him well when physical ailments hit. In 1730s, he lost vision in his right eye. Apparently an infection got loose, something we could probably cure with just an antibiotic. But it not only cost him his vision, it destroyed his eyeball. His whole eye was deformed, and so he just had no use of his right eye. So his productivity goes down, right? Wrong. Doesn't bother him. He keeps going. And continues until 1771, when he lost vision in his left eye. This was a cataract. 1771, they tried eye surgery. And you don't even want to think about eye surgery in 1771. It was painful, and it failed. And so Euler is essentially blind. So his productivity goes down, right? Wrong. It goes up. He actually gets more productive when he can't see. What he would do is he would go into a room, there'd be a table of scribes, and he would just start spouting his mathematical papers, and they'd be writing furiously. Euler could think up mathematics faster than most people can write it. If a new paper came in and he wanted to know what was going on with Lagrange or something, they'd read it to him. He would hear it with this incredible memory. He could see it in his mind's eye and absorb it very well. Euler, thus, is the great inspirational story from the history of mathematics. He's someone who is confronted with a disability and doesn't let it beat him. He is the Beethoven of mathematics. You know, Beethoven composed music he never heard. Euler was producing mathematics that he couldn't see. And if you don't believe me that he was productive even though he lost his vision, let me just indicate that in 1775 he produced over 50 papers and he was blind. So Euler was incredibly productive even with the blindness. This idea of producing a lot of papers feeds into the next slide. His mathematics is distinguished by its quality and its quantity. Really distinguished. Both of these are superior beyond imagining. Let me address the quantity first. Nobody ever did more mathematics than Euler. His output was phenomenal. They tried to publish it all. In 1911, the Swiss Academy of Sciences says, we're going to publish Euler's collected works. The first volume is this. Big heavy book, right? It's heavy to carry around. Well, in 1911, that came out. Another volume in 1912, 1913. They're still coming. They're not done. It's 97 years later, and Euler's work is still coming out. At the moment, the work called the Opera Omnia has 75 volumes. This guy has 74 cousins, all of this mass, and 25,000 pages of mathematics. And nobody's quite sure when they're going to finish this. I mean, it's going to be deep into the 21st century. The grandchildren of the original editors of this are old. and it's still coming out. So the quantity of his work is breathtaking. Here's one other indication of that. After he died, there was a backlog. You know, there were papers still in the chain, papers still on his desk. It took decades to clear the backlog, and after he was dead, he published 228 papers. Now, trust me, that's more than most living people could publish. Euler published more mathematics dead than anybody else. So the quantity of his work, top-notch. But the quality of his work was just as good. You know, if he had done a lot of stuff and it was just drivel, we wouldn't be remembering him here tonight. The quality of his work is extraordinary, and although that's a little harder to measure, maybe. So what I did was this. I went to the online dictionary called MathWorld, and I typed in Euler, and then any term in mathematics that carries his name came back as a hit. And you know, if it's in the dictionary, it's really important. Something that's not just an insignificant little result, but something so great that it's got his name on it, and it's in the dictionary. So I typed in Euler, and I got 96 entries. 96 things in mathematics are named after him, from the Euler line to the Euler identity to the Euler product sum formula. Most branches of mathematics have something named after him. And just for comparison's sake, Gauss, 70. Cauchy was a piker, 33. And some people fare even less well. So, you know, this guy was incredible. He's so incredible, he even has his own comic book. There's an Euler comic book that Berkhauser put out, a graphic novel about his life. So, how cool is that? Right? Okay, well, so that's Euler. Now I want to start showing you some of the things he did that made him famous. Here's one that really is important. The number E, 1748, Euler. And here it is. There's the document in which E appears. And you see it there in the middle of the page. He says, for the sake of brevity, we will use the letter E to stand for the number 2.7182818288459. Euler loved calculating long strings of decimals, so there it is. He says, which therefore denotes the base of the natural or hyperbolic logarithm. So he knows E is important. He knows it's the base of the natural logarithm. And you want to calculate it at home? There's how you do it down there at the bottom. 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. That converges very fast. And if you know the series expansion of e to the x and you put in 1, sure enough, that's it. So Euler gave us E. If he had done nothing else, that would warrant a sentence in the math history books, but he did so much else. Here's one, same year, Euler's identity. Wow. I hope everyone's seen this. E to the ix equals cosine x plus I sine x. A very amazing formula. A strange connection between the exponential function and the trigonometric functions, between real numbers and complex numbers, all in one fabulous formula. Here's how he published it. That's from his work. He wasn't using I, so he wrote e to the plus v times the square root of minus 1 is equal to cos period v. That's because this was an abbreviation for cosinus, so you had to put a period there in those days, plus the square root of minus 1 times the sine of v. So there it is in 1748. Now, anytime anybody shows you Euler's identity, they do the next thing. You kind of have to. Math teachers are required. In which case you get e to the I pi equals cosine pi plus I sine pi. Sine of pi is 0, cosine pi is negative 1, e to the I pi is negative 1. Bring the 1 over, and you get this amazing equation. E to the I pi plus 1 equals 0 falls right out of Euler's identity. Now, math teachers at this point will always say the following. They will say, this is an incredible link among the most important numbers in mathematics. If you were going to have a party and you wanted to invite the 5 most important numbers to your party, who would you invite? We'd invite 0, right, the additive identity. You'd invite 1, the multiplicative identity. If you want to do calculus, you invite E. If you want to do geometry, you invite pi. If you want to do complex numbers, you invite I. 1, 0, E, I, pi, the dream team of numbers right there. And they're all in that one equation. Right? It's amazing. It's amazing that there is an equation that links them, actually. And it's amazing that it's such a simple consequence of Euler's identity. Back in 1988, the journal Mathematical Intelligencer did a survey of the world mathematical community asking people to vote for the most beautiful result in mathematics. And you'd send in your postcard. What's the most beautiful result? It was American Idol for math formulas. Of all the mathematics ever done, this one is the most beautiful result ever. And it's from Euler. It's so beautiful that it inspired someone to write a poem, which I shall now inflict upon you. Somebody wrote, e to the I pi plus 1 equals 0 made the mathematician Euler a hero. From real to complex, with our brains in great flex, he led us with zest, but no fear. So that's something else Euler did. How about this? Euler's polyhedral formula. 1752, he tells us that V plus F equals E plus 2, where we're talking about polyhedra, solid figures with polygons as faces, like a cube, and where V is the number of vertices, F the number of faces, E the number of edges. And this amazing relationship holds. Like for my cube, V, the number of vertices is 8, right? 4 corners, top and bottom. F faces is 6. Think of a dice or die. 8 and 6 is 14. Number of edges, 4 around the top, 4 around the bottom, 4 vertical, 12 plus 2. Bingo, it works. But what Euler realizes is it works not just for cubes, but it works for icosahedra, dodecahedra, and a wide, wide collection of solid bodies. It's this amazing link. In that Math Intelligencer survey of the most beautiful results in history, this was number 2. So Euler has the top 2 slots, all to himself. And he himself was a little more circumspect about this. He wrote, I find it surprising that these general results in solid geometry have not previously been noticed by anyone, so far as I am aware. Kind of a surprise. Something this simple had escaped notice. But of course, there hadn't been an Euler before to notice it. So that's pretty good. What else? Well, there's the Basel problem. So the year is 1734 when Euler solves this great challenge. And here's what it is. Back in 1689, Jakob Bernoulli, who was Johann Bernoulli's brother, Johann being Euler's mentor, challenged the mathematical community to find the exact sum, whoops, got to go over here, of this infinite series. And he issued the challenge from Basel, where Jakob was, so it became known as the Basel problem. What's the exact answer? What is 1 plus a fourth plus a ninth plus a 16th? See what we're doing? We're taking the whole numbers, squaring them, inverting them, adding forever, infinite series. What's it come out to be? Well, Jakob couldn't figure it out. Johann Bernoulli couldn't figure it out. Leibniz couldn't figure it out. It was hard. Nobody could figure it out. They knew it converged. They knew it converged to something less than 2, but they wanted the exact answer. And the first person to get that exact answer would be famous. And that person was Euler. And the answer, you know the answer? Pi squared over 6. That is a strange answer, right? That is, in fact, correct. And Euler gave at least 4 different proofs in his career that it really is pi squared over 6. One way to fill up 75 volumes is to keep doing the same thing multiple ways. Amazing result, right? In the Math Intelligencer poll of the most beautiful formulas of all time, this was number 5. So Euler has topped the charts like the Beatles used to do when I was a kid. He had 1, 2, and 5. All right, what else? Well, the bridges of Königsberg. Probably you know this one. This was sort of famous. This is a picture from one of Euler's papers showing the town of Königsberg, with the river flowing through, dividing around that island at A, and then splitting and going around the landmass at D. And you can see the little bridges connecting various pieces of land. Now, the story is that the good burghers of Königsberg on Sunday afternoon would take a stroll, and the goal was to walk around here and cross each bridge once and only once. What we now call an Euler path. But they couldn't. Every time they tried it, they either missed a bridge or they found themselves crossing a bridge they'd already crossed. So they're perplexed. What's going on here? And so they asked the mayor. I don't know why, but the mayor of Königsberg, and he didn't know, of course. So he wrote to Euler, and he says, can you explain this? Is this possible? And Euler proves that it isn't. This particular configuration. You cannot walk around here and cross each bridge once and only once. And then Euler shows when you could do it. He drew some other neat little pictures with complicated bridge arrangements, which would work. And nowadays we look at this and see this as the first instance of what's now called graph theory, where you have vertices or nodes connected with edges. The land masses are the vertices, the edges are the bridges. And a whole subject is getting born here as Euler approaches this problem. Now, he himself, a little more circumspect. He said, this solution bears little relationship to mathematics, and I do not understand why to expect a mathematician to produce it rather than anyone else, for the solution is based on logic alone. He saw it as like a puzzle, and he didn't think it was math. He didn't need integrals or anything. Now, don't tell your graph theory friends that he said this, okay? Actually, if he were to come back today and see what has happened to graph theory, I'm sure he would recognize it as mathematics. All right, anything else? Well, yeah, how about geometry? Plain geometry. Now, you would think that that had all been discovered, by the time Euler got here. Euclid had done all his geometry, Archimedes. Was there anything left to discover about triangles? Well, actually, 4 big fat volumes of Euler's collected works are geometry. He discovered lots of stuff. And one of the things he does is the Euler line. And you may or may not have ever seen this, but if you have a triangle, any triangle, it could be isosceles, it could be right, but it needn't be anything special. You can consider the intersection of the altitudes. Remember, the altitudes go from each vertex perpendicular to the opposite side, and they all go through a point, which is called the orthocenter. You can consider the intersection of the medians. Now, the median goes from each vertex to the middle of the opposite side, and those are concurrent. They all go through a single point called the centroid. And you can consider the intersection of the perpendicular bisectors. So if you take each side, take the bisector, and drop a perpendicular, those meet in the point, which is called the circumcenter. It's the center of the inscribed circle. These points were known to the Greeks. These aren't special or anything. They'd been around a long time. Now, I'm going to try to do this with my PowerPoint. Let's hope this works. There's a triangle. I want to look at the intersection of the altitudes from each vertex perpendicular to the opposite side. So there's my altitudes, kind of perpendicular, and they all meet in that point, the orthocenter. Okay? So we'll leave that there and get rid of that stuff. Okay. Now, I want to get the intersection of the medians from each vertex to the middle of the opposite side. So we want to do the medians, and here they come from the vertex to the middle of the opposite side, and they meet in the point. Yeah. Get rid of that. And then I want the intersection of the perpendicular bisectors. So here comes, there we go, perpendicular bisectors. Split each side, put up the perpendicular. They meet in a point called the circumcenter. And what do you see? They line up. No one had seen that. Euler proves that no matter what the triangle, these 3 points will fall on a line, which is now, in his honor, called the Euler line. It was an amazing piece of geometry that had escaped all the great geometers in the past. And Euler showed something else. The ratio of those 2 segments is always 1 to 2, exactly. That the centroid is half as far from the circumcenter as it is from the orthocenter. It's a neat piece of geometry. In the subsequent century, lots of interest is devoted to plane geometry. And I think part of it is because Euler thought this was important enough, and he found interesting things. And so you see a renaissance of geometry in the 19th century. Okay, what else? Well, how about number theory? Now, Euler was one of the great number theorists. 4 big fat volumes of number theory. I want to show you something I like. This is not the most important thing he did in number theory. You know what number theory is? It's the study of whole numbers, primes, composites, that sort of thing. This isn't the most important thing he did, but it's just kind of neat. It's a definition that had been around that said 2 whole numbers are amicable, friendly, if each is the sum of the proper whole number divisors of the other. Now, that needs an example, right? Okay, so how about an example? How about 220 and 284? If you ever see this, this will be the example you see, I promise you. So what I want to do is look at the proper divisors of 220, by which I mean whole numbers that divide evenly into 220 but aren't 220. That's what the proper means. It's less. So if you collect them all, there they are, 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. That's all the proper divisors that 220 has. And you add them up, and trust me, you get 284. Now you take the proper divisors of 284, all the whole numbers that divide into 284, 1, 2, 4, 71, 142. 284 does, but we don't count that. It's not proper. Add those up, and you get 220. Each of these is the sum of the proper divisors of the other. It's totally useless. But it's intriguing, right? If you're a number theorist, you will be intrigued by this strange reciprocity. I have a friend, this is the truth, when he married the love of his life, he gave her a keychain with the number 220 on it, and his has 284 to represent their amicability, their eternal friendship. It's really sweet. Nerdy, but sweet, right? Okay. Now, here comes a brief history of amicable numbers. It's a short history. The Greeks knew that pair, 220 and 284. They knew it somehow. And remember, the Greeks, the Pythagorean philosophy that underlay Greek mathematics sort of exalted the role of whole numbers, sort of these metaphysical entities. So the Greeks thought this was really spectacular, and they sought another pair, and they could find no others. They couldn't find any more, that's all. Nobody finds any more until the 9th century Islamic mathematician, Tabat ibn Qura, who finds a rule that generates 2 more pairs. So there was the Greek pair, and he found 2 more. However, this rule apparently didn't make it to Europe after the Renaissance. So the folks in Europe didn't know that Talbot had been down this path. And so they thought there was just 1 pair. And in 1636, the French mathematician Fermat finds another pair. It's those 2, 17,296 and 18,416. The sum of the proper divisors of 17,296 is 18,416, and vice versa. Exercise for the reader. You can check this. Guess what? That was one of Talbot's numbers, actually. Fermat had gone down the same path. He didn't know it. In 17th century France, there was a great mathematical rivalry. Fermat had an opponent, Descartes. They hated each other. And here is Fermat finding a pair. So now Descartes has to find a pair to prove his worth. And he goes to work on it, and in 1638, he finds that pair. If you really loved your wife, you'd give her a keychain with that number on it. Guess what? That's the other one of Talbot's numbers. These 3 are the low-hanging fruit of amicable numbers. And so Descartes and Fermat were just going down a previously trodden path. So now it's 1638, 3 pairs are known. 100 years later, 3 pairs are known. That's it. These are very hard to come by. When Euler's alive, only those 3 were known. And so he thought, well, maybe I should give this some thought. And he worked on it, and he found 58. In a 1750 paper, he finds 58 pairs. So the world supply went from 3 to 61 with 1 person. Now, this is what Euler would do to a problem. He'd just blow it out of the water, He increased the world supply of amicable numbers by a factor of 20. How'd he do it? He saw a pattern that no one had seen, and it allowed him to just sort of generate these things willy-nilly. Great insight. Euler also did applied mathematics. In fact, more than half of his 75 volumes are in things like mechanics, optics, acoustics. I'm not talking about that tonight, but let me just show you this cool little picture I found in one of his papers where he's talking about a pump that he has invented. So he did applied math. And then while we're looking at pictures, how about this? Ever seen those before? Venn diagram. Yeah, that's a Venn diagram, right? We all know the little circles to connect ideas. No, that's not a Venn diagram. Venn lived in the 19th century. I took this out of Euler's work in the 18th century. Not a Venn diagram. We should call this an Euler diagram. However, if we do this, Venn is gone, right? What else did Venn do? So, Euler doesn't need this, for his credibility. So I think we'll let Venn keep his diagram. And then before I get to my proof, one more thing. I just find this intriguing. This is not important particularly, but it's a curiosity, we'll say. Back in the 18th century, the issue of factoring polynomials was important. And the question was, could all polynomials be shattered into first and second degree pieces? I'm talking about real polynomials and real factors. So, if I gave you x to the 4th minus 1, 4th degree, you could break it into x squared plus 1, x squared minus 1, 2 quadratics, and then further break the x squared plus 1, the x squared minus 1 into x plus 1, x minus 1. No complex numbers here, just real numbers. So there's a 4th degree that can be broken into real first and second degree pieces. The question was, is this at least theoretically possible for all real polynomials? If you know the fundamental theorem of algebra, you can see that's what this is in its real incarnation. But people didn't know the answer. It was up in the air. If it's true that such a decomposition is possible, you had to supply proof. But if it's false, you just need one counterexample that can't be factored. And guess what? Nicholas Bernoulli, who was Johann's son and Jakob's nephew, wrote to Euler and said, I found a 4th degree that cannot be factored. So that answers the question. This 4th degree polynomial, x to the 4th minus 4x cubed plus 2x squared plus 4x plus 4, is irreducible. It cannot be factored down. Case closed. Well, wait a minute. Now, Nicholas Bernoulli couldn't factor it, but that doesn't mean it can't be factored. Euler saw how to do it. He broke it into 2 quadratics, this one and this one. Now, two issues here. First of all, that can't be right. Look at these quadratics with square roots embedded within square roots. Are you telling me those two things multiply together to give that simple-looking fourth degree on the top with just integer coefficients? Well, I confess that one rainy afternoon, I multiplied these back together, and all the square roots cancel. It really works. So the one fact that's amazing is this is right. This is true. The factorization problem from hell, right? Second question, how did he do it? Is this finally proof that Euler is from the planet Coosbane, that he's not human? Well, no, because when he tells you how he did it, you see it. Oh, yeah, I see. That was very clever. I could have thought of that, you say. But Euler was Euler. So there you go. All right. Well, now, we've done our little survey. We got time to do a proof, an Eulerian proof. I think if I don't show you an actual proof with the detail, I'm kind of cheating you. I could stand up here and tell you Van Gogh was a great painter, but at some point you want to see a picture, right? I tell you Euler was a great mathematician, but at some point I got to show you Euler in action, and so here comes. The issue at hand is the partitioning of numbers. Partitioning. And let me first of all introduce a little bit of notation here. D of n is the number of ways of writing n as the sum of distinct whole numbers. D of n is how many ways to split n into the sum of distinct whole numbers. Well, we need an example, right? Every time you get one of these definitions, you want to see an example. So how about 5? Let's take a look at 5. So the question is, how many ways can I split 5 up into different size pieces? One of them I'll just take 5. All by itself. We'll call that a decomposition, sort of the unitary decomposition. How about 4 and 1? That's 5, and they're different. How about 3 and 2? That's 5, and they're different. Any more? Well, you could do 2 and 3, but hey, that's the same as 3 and 2. We won't count that. You could say 6 plus negative 1 is 5, but you don't want negatives here. These all have to be whole numbers, so we can't count that. 1.5 and 3.5 is 5, and they're different, but they're not whole numbers. I think that's it. Okay, so how many ways can you write 5 as the sum of distinct pieces? I think that's where we were. 3. 3 ways to do it. 5, 4 and 1, 3 and 2. So we're going to say d of 5 is 3, the number of decompositions into distinct pieces. Okay? I'm sorry? No, it doesn't have to be 2 distinct pieces, just distinct pieces. Okay, so there's that. Now, let O of n be the number of ways of writing n as the sum of not necessarily distinct odd pieces. So the same issue, decompose, but this time the pieces all have to be odd, even if they're repeated. All right, well, let's try that example, 5. I could write 5 as 5 all by itself. There's one way. I could do, now these all have to be odd. How about 3 and 1 and 1? That's 5, and they're all odd. Now I repeated the 1, but that's okay for this game. And one more. What else? 1, 1, 1, 1, 1, yeah. And that's all. So how many ways to do this? D of 5 is 3. There's 3 ways to do it. Excuse me, O of 5 is 3. All right, another example. I think we need another example, especially since the screen went out here. So let's try 8. All right, so first issue, distinct summands. Break it up into distinct pieces. 8. Well, there's 8 all by itself. 7 and 1. That's 8, and they're different. 6 and 2, bingo. 5 and 3, bingo. 4 and 4, no, because they're not distinct. They're the same, so I can't do that. But I could do 5 and 2 and 1. Those are all different. That adds up to 8. And I can do 4 and 3 and 1. Those are all different, and that adds up to 8. And that's it. So 1, 2, 3, 4, 5, 6 ways to break 8 up, so D of 8 is 6. Let's do O of 8. Let's break it into odd pieces. 8. How about 7 and 1? Odd pieces. How about 5 and 3? Yeah. That's 8. They're odd. How about 5 and 3 1s? Yeah. Let's see, what else? 2 3s and 2 1s? That's 8. 1 3 and 5 1s? Yep. And 8 1s. Right? So there's all the decompositions of 8 into odd pieces. How many? 1, 2, 3, 4, 5, 6. So what we know is that d of 5 and O of 5 were both 3. They were the same. D of 8 and O of 8 were both 6. Those are the same. Is there something going on here? Well, in 1740, Philippe Naudet, a French mathematician, wrote to Euler and asked him about partitioning, about breaking numbers up like this. And within days, Euler has sent back a proof that d of n is always O of n, for all n. And he apologized for the delay caused by the bad eyesight I have been suffering. And so this was a turnaround, almost instantaneous turnaround. Given the mail in the 18th century, that's kind of instantaneous. So I want to show you his proof. I don't know if you know this. The number of ways of writing a whole number in terms of distinct summands is always the same as the number of writing it in terms of odd summands. And Euler proves this for all integers at once. It's one proof fits all. So let me show you the proof. So here's the theorem. For all whole numbers n, d of n equals O of n. Now, his proof is built into 3 little pieces. So we just have to get through these 3 pieces, and we see it. First piece, he says, I'm going to introduce that. P of x equals 1 plus x times 1 plus x squared times 1 plus x cubed, 1 plus x4, 1 plus x to the 5th, an infinite product of binomials. Why is he doing this? Hang on. But this is what he wants to do. Okay? So that's P of x. Now, what do you do with this? He says, let's multiply it out. But there's infinitely many terms. That's all right. That never bothered him. So we're going to multiply this out. Now, you know how multiplying works with binomials. Each binomial contributes one of the 2 terms to the product. What's the constant term going to be here if I multiply this out? 1, right? Each term, there'll be a 1 times a 1 times a 1. So we're going to start with a 1. How about x's? How many x's can come out of this? Well, look, that first term has an x in it, and it can hit all the other 1s, and there's no other source of an x. So you're just going to get an x. X squared, that x squared can hit all the other 1s, and you'll just get 1x squared. This is looking kind of boring here, but things get a little richer now. For x cubed, there's 2 ways to do that. The x cubed in the third term can hit all the other 1s, or I can get the x squared times the x to give me a second x cubed. And I'm going to write it this way, just to see where these are coming from. The x cubed plus the other guy is coming from the x squared times the x. X to the 4th, you're going to get 2 of those. The x to the 4th all by itself, and the x cubed times the x. And one more, x to the 5th, 3 of those. The x to the 5 all by itself, the 4 and 1, the 3 and 2. Look at those exponents. Seen them before? 5, 4 and 1, 3 and 2. Those are exactly the decompositions of 5 into distinct pieces. There were 3 such decompositions. There's 3 x to the 5ths. And you can see where they're coming from. And you see why they have to be distinct, because look at p there. It has all different powers in the different terms. You'll never get a repetition. So by thinking through this, Euler realized that p of x, if we want to write it out as a series, is 1 out front plus the sum as n goes from 1 to infinity. And how many x to the n's are there going to be? D of n, precisely as many as there are ways of writing n as the sum of distinct pieces. So like, how many x to the 8s are there going to be here? There's going to be 6 x to the 8s, and they're going to correspond to the 6 decompositions of 8 into distinct summands. So there's the first formula, first part of the 3. That's p of x. Okay? Now, I'm going to remove this, but it'll be back in a minute, but it's going. The next piece requires one little prerequisite. So this is the one thing I'm not going to prove, but I hope you all remember this. The sum of an infinite geometric series, 1 plus a squared plus a cubed. If this goes on as an infinite series, the sum is 1 over 1 minus a. Right? And I hope people remember that. And there are conditions here to worry about, but he didn't worry about it. If you don't like this, if you want to know where this is coming from, do long division on the right, you'll get the series, or better yet, cross multiply, and you'll see it works. So I'm going to need this infinite geometric series formula. In fact, I'll put it up here at the top. And now, second part of the proof, we introduce q of x to be that. 1 over 1 minus x times 1 over 1 minus x cubed times 1 over 1 minus x fifth, and so on. Why? Hang on. Now, what Euler says to do with this is a bunch of reciprocals with the odd powers. He wants to write them without denominators. So you see that first guy, 1 over 1 minus x. If I use the geometric series formula, I can write that as a series. You know, usually we go the other way with that top formula. We have the series and we want the sum, but there's no reason why we couldn't start with the sum and turn it back into a series. So 1 over 1 minus x, I just let a be x, and I get 1 plus x squared plus x cubed. The next term also fits the pattern. 1 over 1 minus x cubed. You let the a be x cubed, and you'll get 1 plus x cubed squared plus x cubed cubed. So there it is, 1 plus x cubed, x6, x9. The next guy, 1 over 1 minus x to the fifth, let a be x to the fifth, and you'll get 5, 10, 15, 20 as the exponents. So that's what q is. OK, one more thing I want to do with this. Instead of writing that as that x, I'm going to write x to the first. Instead of the x squared, I'm going to write 1 plus 1. Instead of x cubed, 1 plus 1 plus 1. I'm going to break these up into equal pieces. And the second guy, 3, 3 plus 3, 3 plus 3 plus 3, 5, 5 plus 5, etc. So if I do that, then q will come out to be, remember the first one was 1x, x squared, x cubed. I just put the 1's in. The next one, 5, 10, or 3, 6, 9, 12 becomes 3, 3 plus 3, 3 plus 3 plus 3, 5, 5 plus 5. So that's what q is. Okay. Now, I have infinitely many infinite series this time. This is worse than p. But multiply it out. So we're going to multiply it out. All right, so here goes. Multiply it out. What's the constant term? 1. Every piece will contribute a 1. We'll start with a 1. How about x's? The only x I'm ever going to get out of this is when that x to the first hits all the other ones. There's no other source of an x, so you'll just get an x to the first. X squareds, well, that x to the 1 plus 1 can hit all the other ones, but there's no other way to get an x squared, so that's how we start. But there's more than one way to get an x cubed. The x to the 3 in the second term can hit all the other ones, or there's an x to the 1 plus 1 plus 1 that can hit all the other ones. So there comes 2 x cubes, and I'll show you where they come from by writing the exponents in that form. X to the fourth, I think there's 2 of those. There's a 3 plus 1, and there's a 1 and 1 and 1 and 1. And one more, x to the fifth. Where is this coming from? Well, there's going to be an x to the 5, an x to the 3 plus 1 plus 1, and an x to the 1 plus 1 plus 1 plus 1 plus 1. Look at those exponents. 5, 3 plus 1 plus 1, 1 plus 1. What are those? Those are the decompositions of 5 into odd summands. These have to be odd because look at the top line. Everything up there was odd. You're putting together odd pieces. They might repeat, but they're odd. Every such decomposition will give me another x to the fifth. Everything that came out here on x to the fifth was built out of odd summands. How many x to the 8s are there going to be in this? 6, based on the 6 decompositions of 8 into odd summands. And so what Euler has realized is that q of x, which is where this started, is 1 plus the sum. N goes from 1 to infinity. And how many x to the n's you're going to get? O of n, the number of ways of breaking n into odd pieces. So there is the second part of the proof. Okay, so now, third and final part. And let me just review here. We'll take a breath. Okay. P of x was 1 plus x times 1 plus x squared times 1 plus x cubed. And he saw that that was 1 plus the sum of the d of n x to the n. Q of x was this different thing, 1 over 1 minus x times 1 over 1 minus x cubed, 1 over 1 minus x to the fifth. And he showed that that was 1 plus the sum of the O of n x to the n. Now, it's been so long since we started this theorem, I forget what we're trying to prove. We're trying to prove that d of n is always equal to O of n. And what Euler said was, if p and q were the same, which they're not, but if they were the same, then when you wrote out the series, all the coefficients would have to be the same. D of 1 would be O of 1, D of 2 would be O of 2. These would have to match up perfectly, and you'd be done. Your proof would be over if only p and q were the same, which they're not. So let me write that up there. To prove that d of n equals O of n for all n, we need only show that p equals q. Everybody see how that would do it. If p and q are the same, the series are the same, the coefficients are the same, we can go home. But they're different. They're different. Or are they? Euler says they're the same. They're the same. And if I can show you that, proof's over. So why are these the same? They look different to me. Here's what Euler says. Remember P of x. It was 1 plus x times 1 plus x squared times 1 plus x cubed, etc. And there they are, and I sort of moved them apart. I need a little elbow room here. That goes on forever. Turn this into a fraction. Ta-da. Okay. In the numerator, I'm going to multiply by a 1 minus x. Well, if I do that in the numerator, I must do the same in the denominator. So there. Still P of x. I haven't changed anything. I could cancel this back out. Up there on the top, I'm going to put a 1 minus x squared. Down below, 1 minus x squared to keep it equal. Up on top, 1 minus x cubed. Down below, 1 minus x cubed. 1 minus x4, so on, so on, so on. So you do this forever. All those could be canceled. It's still P. All right. Now, look at the first two terms in the numerator. 1 plus x times 1 minus x. What's that? 1 minus x squared. The first two terms up there, whoops, here we go. 1 plus x times 1 minus x, take out 1 minus x squared. The next two, 1 plus x squared times 1 minus x squared, that's 1 minus x to the fourth. They take that. 1 plus x cubed, 1 minus x cubed, takes the 1 minus x to the sixth. Away you go. What's left in the numerator? 1. What's left in the denominator? All the odd ones. And so what you get is 1 over 1 plus 1 minus x times 1 minus x cubed times 1 minus x fixed. And that's q. P and q are the same, and hence d of n equals O of n for all n. QED. Pretty good, I think. I will pass your applause to Professor Euler, who deserves it. And he does all this in a few days, and his eyes are hurting. This is where the whole theory of partitioning of numbers starts, right here. And it's now a vast branch of mathematics with really great work going on. It started right there. So I will leave you with two quotations, which I think are fitting. One is from the mathematician Frobenius. And he looked at things like this, and he said, Euler lacked only one thing to make him a perfect genius. He failed to be incomprehensible. And one of the things I like as I read through Euler is that you can really understand what he's doing. It's not so complicated. And he's a very good expositor. He tries to make it clear, and he is never incomprehensible. The other quotation I don't have a source for, but I like it. I think it's fitting. Somebody said that talent is doing easily what others find difficult. Genius is doing easily what others find impossible. And I think by that definition, Euler is a genius. He could do the seemingly impossible, and he did it throughout his long and illustrious life. Certainly a good reason for us to give a tribute to him, and I'll leave with a shout out, way to go, Uncle Leonhard. Thank you.
Well, Bill, that was a really fine talk. I think we can probably take just a couple of questions. Before doing so, I'd like to express my thanks to Harvard University for allowing us to host this talk here. So maybe a couple of questions for Bill, and then we'll be out of here.
Yes?
Did Euler set the calculus into present modern phase form that all the calculus textbooks go back over?
The question is, what was Euler's influence on the calculus? He wrote a gigantic text on calculus. His differential calculus book was this big, and his integral calculus book was 3 volumes. So, if you think your calculus book is big today, you should have seen Euler's calculus. For the sort of first-year calculus, yes, we sort of model our textbooks on his, except they're not that big. But he never did the epsilon delta stuff, the analysis that you hit beyond calculus, that sort of limit-based calculus. Limits weren't around when Euler was working. He worked with infinitely small quantities in a kind of philosophical, metaphysical world that we now either don't like or we put it over in non-standard analysis. But the epsilon delta stuff that you know if you've taken analysis comes with Cauchy in the 19th century. So in that sense, his calculus book isn't a modern one. But the basic topics are pretty much accurate. Oh, that's okay. You can go out now. Yes?
If you look at those books, what do you learn about his mode of working? In other words, I understand that some writing mathematicians don't show you how they came at something. They just perfect and show the perfect ending.
Yes. Right. The big, you get the question, does Euler supply a lot of detail about his thought processes? And the answer is yes. The two models are Euler versus Gauss. Euler will write and tell you what he's thinking. I tried this, it didn't work, he'll tell you. Oh, and then I tried this, oh, that didn't work either. And then I tried this, and wow, it worked. And you really can see him thinking. Now, he could do this because at the St. Petersburg Academy and the Berlin Academy, he had the right to publish anything he wanted without an editor. So he could just be as expansive as he wanted, and nobody was going to cut. So that doesn't work anymore. The other side of the coin is Gauss. Gauss would take out everything, all the intermediate thought, and just leave the basic, beautiful structures, but which makes Gauss much harder to figure out. You know, he doesn't help you along. People criticize Gauss. They said Gauss was like the fox that walked through the sand and dragged his tail behind him to erase the footprints. You know, you didn't see how he did it. You didn't see how he passed this way. Gauss responded, he says, yes, but the architect of the great cathedral doesn't leave the scaffolding up. You take that down and you just leave the gem of the idea. So if you want to see somebody that helps you understand, Euler's your guy. And we should all be grateful for that, I think. Yes?
I was reading today about a book on Einstein and all the mistakes that he made, which we don't hear about very often. I'm wondering if Euler made any big mistakes that needed to be corrected later on.
He made mistakes, yes. He had conjectures that turned out not to be true. He offered a proof of the fundamental theorem of algebra, that thing about breaking all real polynomials into first and second degree pieces that was flawed, and Gauss caught the error. So he was human. He didn't make too many, though. I mean, in 25,000 pages, everybody can have a couple, you know. But he was pretty good. And very often, when he was working on what we would almost call intuition, you know, he didn't have the rigorous foundations that we have. Yet he got it right time and again. And, you know, you get this sense that he sort of knew more than he was letting on as to how fabulous was his insight.
One more question?
Yes.
Can you tell us something about the letters he sent to a Russian princess? Euler also a poet too?
German princess, yes. No, they weren't poetry, yes. His most popular work, the one that has sold the most copies, is called Letters to a German Princess. And what these are essays on popular science, not so much math, but supposedly he was teaching this young girl about the world. So, you know, why does the sun rise in the east and set in the west? Why is the sky blue? And he'd write these little letters, you know, that went to her, supposedly. But in fact, they got published and in German and French, Russian, and there's an English translation of that. And they're considered very high quality popular science. And you know, not every great genius can write popular science with equal success. And in fact, Euler could do that. So you can go find that in the library if you want. It's neat stuff.
Well, let's thank Bill again for
Thank you.